Yes, we can start, sir.
Okay, thank you. Let me start. Welcome to today's chemistry. Welcome to today's chemistry online class. For today, I'll help you with integrated rate law. I want you to pay extra attention because this part is very much important. Before I start, just ensure that you subscribe to our YouTube channel and follow our Facebook page so that you will be updated or notified whenever a new video is posted. For now, let's start. So now, what do you understand by integrated rate law? Integrated. There's something like that has to do with integration here. So integrated rate law. What do you have to understand about integrated rate law? Sorry guys, my thing is not moving. I suspect is just stuck. Okay, thank you. Okay, so now integrated rate law. Integrated rate law. So what do you have to understand about integrated rate law? What is it? So note that an integrated rate law is an equation that relates concentration of reactant to time. So it relates concentration of reactant to time. It relates concentration of reactant to time. Apart from that, it allows us to calculate what? Concentration after some time. It allows us to calculate concentration after some time. Apart from that, it also helps us to calculate time taken for a reaction. Time taken for a reaction. Not only that, it also helps us to identify the order of a reaction. It also helps us to identify the order of a reaction. So the most important ones that I want you to know is the integrated rate law will help us to calculate concentration after some time. The concentration. Apart from that, the time taken for a reaction. Any question before I proceed to the other part now? On the integrated rate law. No question? Hello? Just want one person or two to tell me to proceed, I proceed. Are you guys still part of class? Chimwemwe, Dines?
Yes, sir.
Any question here?
Yes, sir.
No question? Any question?
No question.
Okay, thank you. So now, let's look at the zero order reactions. You understand? Yes, you will understand. You will understand. So let's look at the zero order reactions. So if you remember, do you remember the rate law for the zero order? Do you remember the rate law for the zero order? Rate is equal to what? What comes here? The rate constant, not so. Then the concentration of the reactant. We are assuming this is a concentration for the reactant raised to the power n. Now we are saying this is a zero order. So our n will be represented by what? Zero, not so. So our rate for the zero order will be what? N will be zero. So according to the laws of indices, anything raised to the power zero is what? 1, not so.
Yes.
So our rate for the zero order is dependent on the rate constant K. This concentration disappears because this is zero order. Yes. So our final one, we can say it's going to be like this. So now you know where this is coming from. From there now, let's look at the integrated rate law. Integrated rate law. Now, this is the integrated rate law. We're interested in this because whatever I'm teaching you here is under integrated rate law. So now, how are you going to come up with the integrated rate law for the zero order? How are you going to come up with the integrated rate law for the zero order? So, I have a video that will make you understand, but here I'm just going to tell you where the integrated rate law is coming from. So, they had to get, you remember, this is your reactant. Your reactant is decreasing with time to form the product. So here, the reactant decreases to form the product, while the product increases. You get not so? Yes. So now, if you remember the reaction rate, the reaction rate for the reactant A. This one is decreasing with time. Since it's decreasing, we are using the negative. For those who have been watching my videos and following, you know where the negative is coming from, because the reactant A is decreasing with time. So therefore, use negative. Rate is equal to what? Is concentration also. So it will be concentration, changing the concentration of what? Concentration A over change in what? Time. So this is how you come up with a rate for this reaction that you are seeing here. So this negative is decreasing with time. And then negative change in the concentration of what? This over change in what? Time. Now, once we have this, we combine it with the rate, the same rate for this same rate. They had to get this same rate here, K. And then here, they had to do dy dx, the integration, dy dx. So here from the rate, they had to do negative dA over dt. You get? So they had to integrate, they combined, in short, they combined these two, the rate law and the reaction rate, and then they integrated. That's why we are having the integrated rate law. So after integrating everything, me, I'm just interested in the integrated rate law for the zero order. So they came up with this equation now, this one here, which is going to give us the concentration like that, which is at T, concentration at T is equal to concentration, the initial concentration 0, and then from there minus Kt, which is the time factor. This is the rate constant and this is the time. So after doing the integration, this is coming out. I have a video just after this same class. You can ask me. I had to show where this thing is coming from. I explained everything. Now we're not interested in that because they won't ask you how where it's coming from, but it's good to know. Is it clear? Are you guys clear on how this integrated law is coming about? They had to get the rate law as well as the reaction rate, and then they integrated. That's why they came up with the integrated rate law. And after they do the integration, do whatever, it gave them this equation. So the integrated law for the first order, this should come into your head. Is it clear before I proceed to the other part? So I want you to take a screenshot of this because we'll be using this for solving. Any question? Hello? Guys, let's interact. Are you clear?
Yes, it's clear, sir.
Okay, so try to take a screenshot for this. I'll ask you for the first order, you just have to master that. Now, let's also look at the half-life. They'll ask you to find the half-life here. Half-life represented by that, meaning half-life, is equal to. So for the first order, we will get the initial concentration, time taken, not so, initial concentration, over what? 2K, which is the rate constant. So this is how they came up with this. Also this one, for this, I'll send you a video where this thing is coming from. I explained and I derived all this using the integrated whatever. So I'll show you where this is coming from. So as at now, when they ask you under the zero order to find the half-life, you need to know that your half-life is equal to the initial concentration, not this concentration at time t. You get? The initial concentration over 2 multiplied by the rate constant. So the rate constant must be given. So try to take a screenshot and master this formula for these two formulas for the zero order. So now let's do this. Yes. So this is the one I'm from showing you where it's coming from. I'm from saying it's coming from the rate law combined with the reaction rate. And then they had to integrate. This came up. So this is a formula that you need to know for the integrated rate law, for the zero order. Apart from that, let's look at the half-life. Half-life is this one here. I'm from giving you. Yes. Apart from that, what else now? What do you have to know? So this concentration which is having this, which means that that's the initial concentration. That zero you're seeing down, that's the initial concentration. What about the other concentration? That's the concentration at time. So the time will be given, concentration at time. You get concentration at what? Time. Apart from that, we also have the K, which is our late constant. So there are questions where they will ask you to calculate for the late constant. Apart from that, let's quickly look at the time. So T is for what? For time. So before we do any other thing, any question from the first part, you are clear for the formula to use when you're told to find the half-life? You are clear on the equation for the integrated rate law before we can solve any question from here?
Yes, sir. We are clear.
Okay, thank you so much. Now, there's a graph. There's a graph. So here, the graph for the zero order is going to be like this. Here, you're going to have, this side is for the concentration. That's why it's concentration versus what? Time. And it's a straight line. It's a straight line. So concentration. So your concentration A plotted against what? Time this side. Yes, then this one can be a zero. Now, this is a negative slope. Have you seen? It's a negative slope. So which means it's falling, it's coming down like that. You get? So this now is the slope you are seeing. The late constant K, the negative K. It's decreasing. You get? Yes, it's decreasing. It's a negative slope. Any question before I proceed? Decreasing, it's falling just like that. Any question here? You guys are clear, not so?
Sasa tumewapatia pano ya chimana kana screen ya nani.
Okay, so I'm saying on this one, when you're told to plot the graph for the zero order, so the graph, how does it look? So here, if you plot it, concentration versus time, so it's going to be like this. So this side, you are going to have your concentration. This side, you're going to have your time. So that's why they're saying it's plotted concentration versus what? Time. And it's a straight line. So you're starting, that's a zero, not so. Yes. And then here, have you seen your late constant is negative? Your late constant is negative here. If you saw the formula, there was a negative there, not so. So it's decreasing. It's falling like that. So it's a slope, the negative slope, the net, which is the negative K, the slope, the negative K, the slope. It's falling. It's decreasing with time. If it was positive, it must be going, starting from down here, going up. Now, the late constant K is negative, which means it's falling, it's decreasing with time. I don't know if you're clear now. Are you clear?
Yes sir, yes sir.
Thank you. Chimwemwe, are you clear? Dennis, Janet, Melly?
It's clear.
Wow, thank you. So let's now answer this question. You guys, I told you to master those questions. So those formulas. I told you to master those formulas. So who can lead for me this question? Someone to lead, then we answer some questions. We see how we can apply this. Yes. Any volunteer to lead the question? No volunteer. Oh, you guys don't know how to read. Someone to lead the question, guys.
All right. So question one. The question reads: a reaction follows zero order kinetics. The rate constant is 0.02 moles per liter per second, and the initial concentration of reactant A is 0.50 moles per liter. A. Calculate the concentration of A after 10 seconds. B. Calculate the half-life of the reaction.
Wow. Here they have even specified or said this is zero order kinetics. So the formula for the half-life as well as for finding the concentration, you use the same integrated law for the zero order. If it's a first order, they will specify and they will tell you. Sometimes they won't tell, but there's something that will make you understand. So let's come up with a data. So can someone tell me which formula we're going to use? Which formula are we going to use for finding the concentration? Yes. Tell me the formula. If you remember, it was what? Concentration at T, not so, is equal to the initial concentration, negative.
Minus
Yeah,
KT.
very good. Yes. Now, here we just have to check what have we been given. So let's try to look for what we see what we're looking for and we see what we have been given. Yes. What have we been given here? What can you notice here? We have the rate constant K, not so. Okay, before that, see, calculate the concentration calculate the concentration of A after 10 seconds. Have you seen that concentration they want is a concentration at T? They have specified. Yes, they have specified 10 seconds. So they have specified. So that's T. You can even replace it with 10. You get? That's T. You can even replace it with what? With 10 if you want. 10. They have specified at 10 the T given time. Yes, I've replaced it. Now, do we have the initial concentration?
Yes.
Yes, what's the initial?
0.50.
Yes, 0.50 more per liter, like that. Now, what else have you noticed here? Do you have the rate constant? Do we have the rate constant?
Yes.
Yes, the rate constant K we have. What's that?
0.02.
Yes, 0.02 more per liter per second. Then what else do we have? Time also, T, which is what? What's the time?
10 seconds.
10 seconds. Then we can just substitute here. So we know that we're looking for this concentration here, which is at 10. Time we have been given is equal to. What's our initial? We have, which is 0.5. Not so. Forget about the units, you can do that later. What's our K? Our K, that's 0.02 multiplied by time, which is 10. Yes. Then let's do this. 0.5 minus. What is 0.02 multiplied by 10?
0.2.
That's 0.9. You just move the decimal. You guys, if you used to dodge the time you are learning these decimals, you can have challenges. Then when you subtract, what are you getting? 0.50 minus 0. What are you getting?
0.3.
0.3. Now this is concentration. What will be the unit? What would be the units? More per?
Per liter.
Was this hard?
More per liter.
Was this hard? Here you keep on dropping your air concentration at T. Now, for the sake of space, there is not. So that's how you do it. Is this hard? Should I proceed to the half-life?
Sure, sir.
Chimwama, are you clear? Dines, Janet?
Yes, sir.
Okay, thank you. Melly. Okay, let's do B. Let's do B. So these things are very simple. Just have to keep on practicing a lot. Yes, just have to keep on practicing a lot. Yes, we'll be done with this topic in time soon. So let's do B. Can someone remember what's the formula for half-life for the zero order? Yes, half-life is equal to what? The initial concentration. I told you to over what?
2.
The rate
Yeah.
constant K multiplied by rate constant. Very good. So from here, let's do this. What's our initial concentration? That's 0.05. Oh, sorry, 0. Sorry. That's 0.50 over 2 multiplied by our rate constant K, which is 0.02. So can someone multiply? We have 0.50 over, what is 2 multiplied by 0.02? That's 0.04.
Yes.
Then once you divide, what are you going to get? 0.50 divided by 0.04.
12.5.
12.5. Half-life measured in what? Seconds. Any question? Is it clear?
Yes, it's clear.
Wow. So that's how you go about the zero order. So you just have to know the formulas for the half-life as well as for the integrated rate law, the one I gave you. Very much important. So we can now proceed to the what? To the first order now. First order. So you can mute your mic. There's someone who's having the mic on. You can mute your mic. Yeah, so now the first order. That was the first law. So the first order, what can be the first law? Can someone remember the first law for the first order? So we know that rate is equal to what? Rate constant, concentration for A, raised to the power n. Then here, since the first order, our n is raised to the power what? 1, not so. So our A as our power is just 1. Therefore, 1, anything is just this A concentration. So our rate for the first order, we're going to have it to be like that. So this means that our first order is dependent on a single concentration, while the zero order was dependent on what? Or is dependent on what? On the rate constant. But for the first order is dependent on a single concentration, 1, because it's raised to the power 1. Is it clear? We're just having one reactant here. So now, this is just what I wanted you to know. For the zero order, it was just dependent on this. Now, for the first, that's 1. Hope you're able to relate and see where this thing is coming from. So this is now what I'm from doing here. So the rate law for the second order is this. It's dependent on a single reactant. Now, what about the integrated rate law? So here also, they had to integrate. They had to get what? The reaction rate. The rate. If you remember, rate is equal to what? Negative change in the what? Concentration of A over change in what? Time. So they used these two. And then they integrated the rate law as well as the reaction rate. They integrated these two. After doing the integration, that's why it's called the integrated rate law, this one. After doing the dy dx whatever, they had to get the integrated law for the second order to be lean. The same formula that we are from, we just have to add the lean. The zero order formula is the same one. Now we're just going to add the lean. You get? So it's going to be lean, time there, yes, concentration at t, and then we're going to have lean, yes, initial concentration, then minus, everything is just the same, but we've just introduced the lean for the second order. Is it clear?
Yes.
Yes. So you can't forget this because the first one there, for the second, just have to add the lean in front of the concentration, the two concentrations. Now, if you want, you can just be using this formula, but let me show you the other one. Just it's the same one. So do you know what we do? We'll subtract the concentration at T, both sides. Subtracting it, okay, let's try to take it this side. Then this side, we're just trying to take it the other side to make it positive. So once we take it this side, it's going to be like this. From positive, it's going to be like this. Once we take it this side, we're trying to subtract. So this one should adopt a negative sign. We're trying to subtract this, both sides. The left-hand side as well as the right-hand side. Don't do it the other way around. Because if you make your K to be negative, then you make things. So it's going to be like this. Lean, which is the initial concentration, we're trying to subtract this both sides. So this when it goes outside, it's going to adopt a negative lean. Is equal to. Now, when we change this also, we try to take it the other way. The negative will go. Therefore, it's going to be a positive. You get? From here, laws of indices. Have you learned about indices or logs? What do you do when you are subtracting logs? The same as you are dividing, huh? Hello?
Yes, sir, it's true.
So, yes. So here, what will happen? Your lean will be like this. Then you're going to have this. It's going to be like this. It's going to change into division because of the subtraction. So it can also be written like this. Is equal to. So I don't know the one you'll be using. If you want, you can use this one, direct one, or you use this one on top here. So whichever, I don't know the one you want. Which one should we be using? Which one should we be using here? Which one do you want? Chimoyomo, you don't, Dinus, Janet, say something.
The
Charlie,
second one, sir.
the second one, eh? Yeah, so I'll be asking
Yes.
you, you'll be telling me. Yes. Okay, hope you guys are okay. Now let's look at the half-life now for the lean. Yes. So for the half-life now, it's going to be like this. Half-life 1/2 is equal to. Here now it's going to be once I told you just after this video, you can send I will send you the video. You can inbox me, send me the video. I'll show you where this thing is coming from. So it's going to be lean of 2 over k. This also can be written lean of 2 when you calculate when you punch, you're going to get 0.693 over the rate constant k. So just use this one direct if you want. Or if you want, you can use this one, but this one is already direct. You get once you have this in numbers, just divide it with your rate constant. That's all. Clear? So that's it. The half-life is there. You can take a screenshot in case I ask you. So before we go to the other part, we solve questions. Any question on this part before we proceed? You guys even just saying proceed or say some repeats or we're not clear. Say something, guys. Are you guys getting something?
Yes.
Okay,
All right, so the question that I have is when asking questions, do they specify that here it is the zero order or the first order?
yes, some questions they specify. Most they specify, but there are questions whereby they don't specify, but a reaction can tell you that this is a second order or first order. I'll show you, I'm sure there's an example just from the reaction.
Sure.
Yes.
Yes, so in terms of the question where I said, just like the way you explained about the zero order reaction, this one, the first order when it comes to a graph,
Oh,
Is it supposed to be?
that's where I'm going, sir. That's where I'm going. So I wanted you just first to see if you're clear on the.
All right, sir. All right.
Yes, for the graph, say something now. We're on the graph now. How is it going to be? What do you think is the graph going to be? What do you think the graph will be? Since it's a negative slope, it's having a what? A negative slope, not so.
And then- yes,
So it's just the same.
yes.
Yeah. So now here concentration, since it's for the second, you use now the lean. Supposed concentration versus what? Time. So this one also is decreasing with time. The slope is falling like that. So the rate constant K is what? Negative. It's falling like that. Clear? Are you clear, sir?
Yes, sir. Very clear.
Very clear. I'm happy. Chimwemwe, Dines, Janet, Muso, is it Musonda? Okay, I should proceed. Should I proceed to the
Yeah,
question
I
now?
can't. I can't see your screen.
Oh,
Um,
who else can see the screen? Okay, what we can do is try to log out and log in first. Network issues. Sorry for that. Who else can see the screen? Are you guys able to see the screen? Dines, are you still part of class?
Yes.
Are you following? Is this part okay? Are you okay?
Yes,
Any
I'm
question?
okay.
You're okay, thank you. What about Janet? Are you still part of class? Musonda,
Yes, sir.
are you following? Like, are you okay on this part also?
Oh,
Why
you
is
can
the
proceed.
why is the slope like the slope? Why is it falling? It's because of the rate constant K is negative.
Negative.
Yes, it's decreasing with time. So for the second order, concentration this side ensure that your concentration is in lean of A plotted against what? Time, like that. Okay, but if it's positive, it must be going up. If it's positive, it must be going up. Negative, it's falling just like that, decreasing. Your reactant concentration is decreasing with time. Your reactant concentration is decreasing with time to form the product. So, okay. What up, Chumom, are you back?
yes.
Can you see the screen now?
Yes.
Let's solve this question now. Lead the question. I want to see if you're able to see the screen. Lead for us.
A reaction follows first order kinetics. The concentration of reactants A decreases from 0.80 mole per liter
Mm,
to 0.2 mole per liter in 30 seconds. Calculate the rate constant for the reaction.
very good. Here we are told to find or to calculate the rate constant for this reaction. And this reaction is a first order. They have specified. So what are we going to do? Let's come up with a formula. Since it's a first order, we need to find or look for the integrated rate law for the first order, which connects the concentrations they have mentioned with a rate constant K. Which formula is that? Yes, let's write it. Can someone remember? Guys. So it's going to be what? Lean. You remember it?
Yes.
What's
Uh,
yes? What should be on top here?
it's the initial concentration.
Yes, over the concentration at T.
Yes.
Exactly, like this one. So once you have this, you just have to collect the data now. Once you have this, correct the data. So let's come up with our data now. Guys, we're told to find K. That's your first thing, the rate constant K. Do we have the initial concentration? Tell me, do you have the initial concentration? What's it? From lead, so the concentration of a reactant decreases from to this. What does that mean? Which one is the initial and which one is the concentration at T? Yes.
0.8
The
is the
initial is
initial.
0. Okay.
Is 0. What? 80. Very good. 0.80. Oh, sorry. And then to this one now. So this one became like the final concentration. From there to this, you get? Now, from here in 30 seconds. So this T, you can even take it to 30 because T it has been given, the time has been given, not so. Yes, at T, so that one is 0.20 more per liter like that. I don't know why I'm putting that thing down. Then what about our time? That's what? 30 seconds. Then we just replace. So we have lean. What's our concentration? Our initial, that's 0.80. Then down here we have what? 0.20. What's our K? K is the one we are looking for. There, that's 30. So let me create some space. Let me create some space so that we utilize this. But is it making sense? Are you able to get something from here?
Yes.
Okay, so this is what we expect. That's good. So now let's do this. Can someone tell me, when you divide these two inside, what are you getting? 0.80 divided by 0.20. You guys don't have calculators? Then 30 times K, that's 30 K. What is 0. You don't have calculators?
4.
That's 4. Then do the lean of 4 on your calculator. Lean of 4. What are you getting? It's 1.3863. You can confirm in case I make a mistake here. Lean of 4 is giving you this on your calculator. Then you divide by what? 30. Also this side 30. You cancel. What is 1.3863 divided by 30? It's giving me 0.0462. Now, this is the net. And for the first order, what can be the units? You remember, I showed you how to come up with the units. This is the net constant. The units differ depending with the order. So if you have been watching my videos, I explained why or where these seconds are coming from. You get? So you need to watch the other videos. Any question on this part? It's clear?
Yes.
How many are clear? Tell me. Should I proceed to the half-life?
Yes, sir.
Yes, I can proceed.
Okay, thank you. Now let's quickly do this. B. Calculate the half-life. So what's the formula for half-life? 1 over 2 is equal to what? 0.693 over what? The rate constant K. Yes. So here now, what was our rate constant? That's 0. What? We found not so 0.462. You divide these two, what are you getting? Mm-hmm. Diners, don't you have a calculator? You're just watching. Janet, Chimwemwe, the Gopara boys. I told you to prepare calculators, huh?
As
So,
for me, I don't have a calculator.
oh, so
14 point
15, huh? 0.0 seconds. That's time. You don't have a calculator? Okay. So that's how you go about this question. Should I proceed to the other question? There are two questions on this, so I just have to solve now the other one. Yes.
you guess that.
I proceed? For those who have been checking your tutorial sheets, I'm sure there's a question which is like this. So let me solve this one, and then the other question will be your task. You get? The tutorial sheet question will be your task. So let's do this now. Can someone lead for me? We start. No one knows how to read here. First, guys, we call it a night. This is the only question that I want to solve then.
In a first order reaction is 45% complete in 600 seconds. A first order reaction is 45% complete in 600 seconds. Calculate the rate constant.
Wow. So let's just start with calculating the rate constant. They have even said this is the what? The first order. Now here, they haven't given you the concentration according to the number, but they have written this thing in percentage. What can you do? So here, if you have been given 45 and it's out of 100, that's a percent. It's out of 100. So your interest is to know the remaining amount, the remaining percentage. So what's the remaining percentage from this?
10%.
Is what?
Oh,
55.
55. Very good. So your interest is to no. So you do 100 minus 45. You're going to get 55. This is now 55 what? You're going to, this is 55%. Yes, because this is a percentage you have used, so that's 55%. Now, are you going to use percentage on the formula? Are you going to use the percentage on the formula?
No.
So what do? You divide this by 100 so that you make it into a fraction. You get? So we'll do this. You are dividing this. So now it has changed. Now time over what? The initial time, like that. So we are dividing now. We're having what? 55. Because that's the time that the remaining, it has been specified at the time, 60 seconds, the remaining one. You get? So that's why this is a constitution at t-time. You have changed, you have flipped. Then the initial, that's 100. So the initial can be represented by 1 or 100. So now when you divide, you're going to get 0. What? 55. So we'll use this now. So I'm saying the initial can be represented by 1 or by 100. So depending the one we are going to use. You get? So if we're using in two percentages, just get your initial to be 100. If you're using it into decimal, like the way we have converted into fraction, then you're going to get our initial to be 1. Is it clear on my explanation? Okay, you will see this. So I'm saying this is the same as, okay, let's do this. I'm saying the initial is equal to what? 1 or the 100, not so? Yes. So when you're taking it to be 100, then you should just get your 55 direct. When you're getting it to be 0, like when you're getting it to be 0.55 in decimal, then your initial should be 1. Are you clear on my explanation? Chimwemu. Okay.
Sir,
Are you clear on
I'm losing.
you're lost?
I'm losing your screen. Then again, I'm getting it back. Swap. I have it, but after some time, I'll lose it.
Okay. Dinus, are you clear on my explanation?
Yes.
Okay, so Chimwemu, you watch the video. Let me just explain first. So, what's the formula you're going to use here first? What's the formula you're going to use? What's the formula you're going to use? The same one for the integrated rate law for the first order. So it's going to be what? Ln of the concentration, which is the initial, over the concentration at T is equal to what? Kt. Now let's come up with our data. Let's come up with our data. So what are we looking for here? That's a rate constant K. What's our time? Our time we have been given that 600 seconds. Then what's our initial concentration? Here now, that's what I was explaining. If you get your initial concentration to be, so like if you get your, we have also the concentration at T. The concentration at T is what? Is the same as this same, the remaining one. The remaining one, which is 0.55. So when we take it into a fraction, then our initial will be 1. If we take it to be 55 direct, 55, the way it is, then our initial will be 100. That's what I was saying, to say our initial concentration is 1 or 100. It depends on how you're going to use the numbers. If you take it into direct, into the percentage, take your initial to be 100 direct. If you take it into like decimal, then it's going to be what? 1. Clear on this explanation now? Even just saying yes, guys. I don't know if you're lost or you're clear, but let's proceed. So what's our initial? That's 1. And then the concentration at T, which is 0.55. What's our K? It's the one we're looking for. What's our time?
600.
Yes. You are clear on how I've explained on the initial, not so?
Yes, sir.
Okay, thank you. That's what I want. I just want to hear yes, sir, with a voice projection. Or the other voice. Is it the... We have 2 types of voices, huh? Yeah, okay. Let me not go into the other biology part. Okay, now from here, let's do this. What is 1 divided by 0.55? Yes,
1.819.
1.818. Yes, very good. Is equal to 600 times K. We're going to have 600 like that. Then do the ln of 1.818. What are you getting? The ln of that. So I'm getting it to be 0.598. Let me know if you're having a different one in case I make a mistake. That's the reason why it's a class. Is this what you are getting also?
Yes, sir.
Now from here, what do? You divide. Your aim is to solve for K, so you divide both sides by what?
600.
Yes. Then your K, your rate constant will be what? Divide that. What are you getting? So I'm getting it to be 9.97 multiplied by 10 to the power negative 4. Then the units, since it's a first order, like that. Is this hard or you guys understood? How is it? How is it? Are you clear?
Yes.
What
I
about
have a
Dennis?
question.
You can
I
ask.
was interrupted at first. Where is the one? Is it coming from the n is equals to one, or
Which one? For the power is the seconds.
the you say you're dividing one over 0.55?
Yes, yes, yes. Once you
Yes.
divide, you're going to get 1.818.
Yes. Now the one is it coming from the n is equals to one for
Oh,
the first order
no.
reaction?
This one is the one I explained to say our initial concentration is equal to 1 or 100, the
Uh-huh.
percentage you get.
Mm.
So now it
Yes.
depends with what you get. So for example, we're having 45. So when we subtracted, we got what? 55 percent.
Yes.
So here, this our initial, if we just get it as a percentage, is 100. You get?
Mm.
Mhm.
Yes.
Now, if we divide, we have to divide this to make it into a fraction. It gave us 0.11.
Mm.
So here now we can't get now the 100% again. That's why now we get the 1. You're
I
clear now?
understand.
Yes. So
Uh,
it depends with the one you use. If you want here, you can get the one for, you say 100 on top, divided by the 55 direct. You still get the same answer. So I'm saying the initial
mm.
can be 1 or 100, depending on what you're using. Is it a percentage? Is it a decimal? If it's a decimal, get your initial to be 1. If it's a percentage, get your initial to be 100%. Clear?
Clear, sir.
Thank you so much. Any other question? Chimomo, you're clear. Dennis, Janet.
Yes.
Okay, so write the rate constant somewhere. This one. I'll ask you to, we'll use it somewhere, I'm sure. I'm sure you have taken note of this. We'll get it. So let me do this. So now let's do B, the last one we go. So here, determine the half-life. Half-life is equal to 1 over 2 is equal to, what should be a 0.693 over the rate constant K, not so? Yes. So 0.693 over, what's the rate constant K? Isn't it the one from solving?
Yes.
It's 9.97 multiplied by 10 to the power negative what? 4. Have you seen that you're not supposed to be forgetting these things? So what if you messed up with the rate constant? Everything will be affected. So divide, what are you getting? What is 0.693 divided by that? I'm getting 0, not 0, so 695 seconds. Is this what you're getting also?
Yes, it is.
Exactly. So that's it. We can proceed now. So now what about this one? Here now they want time. They're saying how long will it take for the reaction to reach 90% completion? So this percent also, there's something here. We need to come up with our concentration from this same percent. So from 90, what's remaining?
It is 10.
Exactly. That's 10. Do you know what this means? So here now, which one do we want? We take it as a percentage or we divide it like the way we did? We take it as a decimal. The decimal, the same decimal. Huh?
We divide.
Yes, we divide. So once we divide our concentration at T, once we divide this by 100, we take it into, so it's going to give us 0 point what? 10, not so.
Yes.
Then what
Yes,
would be,
0.10.
yes, what would be our initial, if you're able to remember? What would be our initial?
It's going to be 1.
Exactly. Yes, you understood. Very good. So now let's come up with our formula here. So it's going to be lean like that is equal to, yes. Then therefore our initial concentration on top over what? Our concentration at time t. Then we replace. So lean, there we have what? 1 over 0.10. What's our rate constant K? Here we are told to find what? Time, not so.
Time, yes.
So what's our rate constant K?
9.97
Yes,
exponents negative 4.
9.97 multiplied by 10 negative 4 multiplied by what? T. Therefore, it's equal to, do the 1 divided by 1 point, oh sorry, 0.10. What are you getting?
10.
10, huh? Okay, very good, 10. Then here, T times that, we're going to get just like that, the way it is. 9.97 multiplied by 10 to the power negative 4. And then the T is this side. So here, let's just do the ln of 10. Hope it's making sense and you're following. So the ln of 10 is giving what? It's giving me
2.3.
2.303 is equal to 9.97 multiplied by 10 to the power negative 4. Then we have T this side. So here we divide both sides by 9.7. So 9.97 multiplied by 10 to the power negative 4. Also this side, 9.97 multiplied by 10 to the power negative 4. You cancel that, then our time t is equal to what? Divide that, what are you getting? 2.30 multiplied by, divided by, you're getting 2,310 seconds. Any question? Hey, any question?
For me, there is no questions. I have understood.
You have understood. I'm happy. I'm dancing here. When you understand, I feel happy because my aim is to make you understand. What about others? Janet, Dines, are you guys clear?
Then I've understood, sir.
You have understood
Yes, sir.
even me. Wow. What about Dines, Janet, others?
It's clear, sir.
Yes, sir.
Wow. I'm dancing. You just don't know the way I'm smiling, you know. And this is your task now from your tutorial sheet. Can you follow this question? So take a screenshot now. I need this. You need to answer. You must answer this. Have you managed taking a screenshot?
Yes.
Thank you so much, guys. And please, if there are others who might be interested, we need more people, you know. So we need more people to join just like that, to encourage us and to boost us. Charlie, though I haven't heard from Charlie. Okay, you guys, have you seen, because of who offered the prayer? Have you seen that the prayer has worked? People have understood. Prayer is powerful. So next time someone will pray. I don't know if Mary is clear, Janet. Okay, you guys, anyone who's having a question in my inbox, and then if you want to catch up, I'm ready to take you back so that at least you understand. So just feel free to inbox me and I'll be able to attend to you. And then for those who have submitted that work for the graph, please, I know you guys, I'll get back to you as soon as possible. Let me just do one or two things. Any other thing before I end class? Hello?
I think the last thing is thank you, sir.
Thank you. Now, see, the third order, can you fail? Take a screenshot, you solve, so that next time, see, take a screenshot of this question, this thing you're seeing. This is a formula, but I want to explain anything, but I just want you also to participate. You have managed?
Yes, sir.
Yes.
Me. This is a task also. You should try this one also. So that we are done. So that next time we'll do the other thing.